coming. I hope you are all enjoying your free vacation. So this is something parallel to the thing I spoke yesterday. It's about, again, music generation and emotion. Can I see how many of you listened to my talk yesterday so that I don't bore you? All right, so not many people know about it. Basically, so it's me, my master student Pedro Oliveira, and my supervisor Paula Viena, and we're all from Universidade in Porto. So the problem that I was facing in my PhD was how can I create music, compose music in a symbolic format using deep neural networks conditioned on human emotions. So the idea is that I have an algorithm and I tell it, okay, write me a piece of sad music or write me a piece of happy music, and it will do it. And I had some feedback from yesterday saying, okay, what's the point of doing that? Actually, my entire thesis is about composing music for videos, so that the user will have any type of video, and then they would have a soundtrack to accompany that video. So how do I match video to music? The music is in symbolic format, so it's also MIDI, maybe some of you have heard about it. It's basically a digital sheet music, so you have this, what the musicians play, and this is in digital format, so it's almost like text that you can see, and the idea that some musicians have to play this later, or you can use computer synthesizers to turn this into audio, but then the sound quality is not as good as some actual musicians playing it. So the problem was, I want to do this from a video, but I don't have a data set where I have the video and the matched symbolic music or the composition. So I cannot do end-to-end learning. I cannot start from video and end up in the music part. So I have to come up with some intermediary ideas. One of them is the temporal aspect. So if the video is fast, the music can be fast. If there are lots of scene transitions in the video, I can synchronize them to some musical segment transitions. And the second idea is more semantic. So if the video is a sad video, the music should be sad, or if the video is a happy video, the music should be happy. So here I'm focusing on the emotional aspect, so I'm using emotion as an intermediary for soundtrack composition. So here we are, we're trying to compose music from emotions using deep neural networks. And we need lots of labeled data to train this. So we need lots of music, and each music should be labeled with a particular emotion, so that I train it, and in the end during inference I can simply feed the emotion and the neural network will generate the music. The problem is there's no large-scale symbolic music dataset with emotion labels. So there are large-scale symbolic music datasets without emotion labels. So here we have two of them. There are hundreds of thousands of songs. And then we have very small datasets with emotion labels. So it's, at most they have 400 songs, which is not enough to train a deep neural network. So what we can come up with is we can actually utilize these last two and somehow label them with emotions. But we cannot do this by hand, there are too many. So we have to come up with an automatic way to label these songs with particular emotions. So one way we can establish correspondence is through song lyrics. So if we have the proposition that the lyrics are somehow accompanying the songs, then they should convey the same emotion. So this is our starting point. So here we have the John Lennon song Imagine. So we have the MIDI, and embedded in the MIDI, in many of them, we have the lyrics. So we can feed the lyrics into an emotion classifier from text, and then we can extract the emotion, and then we can simply pair them up with the music. So in the end, what we will have is the emotion and the music, so it's a label data set. So here the emotion classifier would work and say, this feeling, this emotion here is optimism. So I'm aware that optimism is a much complex emotion, it's not happy, sad, angry. But then the models and the data sets we use, it enables this, so I will talk a bit about this later on. So now we have to train the emotion classifier, because I found some emotion classifiers pre-trained, but they weren't performing very well, so we wanted to train from scratch. And we use this library called Hugging Face. I don't know if any of you heard about it, but it's a very nice library that you have lots of pre-trained models, and you have the code. So even if you don't have much programming experience, you can just go to Hugging Face and play with these models. Alright, so Now we're training the emotion classifier from text. Our model is still BERT. So it's a smaller version of BERT, and it's pre-trained using knowledge distillation, and it's a transformer model. So BERT is like GPT. GPT is from OpenAI, BERT is from Google. They use a slightly different pre-training technique. So GPT was trained for next word prediction, and then Google, they upgraded it basically by using masked word prediction. So you have a sentence, and they would block out some of the words, and then the model will try to guess those words. So you can do the prediction in both ways. So you have actually more dense data to train it. So it's that when you have more data, you usually have better results. And knowledge distillation is quite cool. So it's a way to make the model smaller. So you have, let's say you train a very large model, but Google can train very large models. We cannot. We don't have as many GPUs. So we need smaller models. So what we can achieve is, if you have a very big model, we can use that model to train a smaller model that would perform similarly. The way they do it is, knowledge distillations work like this. So in normal training, you have, let's say you're doing image classification. You have thousands of classes, like cat, dog, whatever. And it's just one image belongs to one class. You see a picture of a cat, and the label is cat. So it's a one-hot vector with only one and 999 zeros. So it's a very sparse vector that you cannot learn much from. You only know that it's a cat, and that's it. But once you train a big neural network, very big neural network, and when you perform inference on, let's say, a picture of a cat, you have an output distribution. So the model doesn't output cat. It outputs a probability for every single potential label. So for cat, it says 0.99. For dog, it says 0.01. But then you have 1,000 probabilities. So it's a much denser representation. And using this small network, they're trying to replicate this dense probability. So it's not trying to match only one label. It's trying to match the probabilities for 1,000 labels. So because you have a very dense output, it's much easier to train smaller neural networks to replicate that behavior of a large neural network. So normally the BERT has 12 layers, and this BERT has half the size. So it has 6 layers, each have 12 attention layers and dimensionality of 768, which is roughly 7 million parameters in total. So we're training this model on emotion classification. And the data set we use is called Emotion. Again, it's a data set by Google. It's one of the largest emotion classification data sets on text. And we have 58,000 graded comments in English, and they're multi-label, which means each sample can have multiple positive labels. So it can be, a text can both be sad and angry at the same time. And these are human annotated with 27 emotion categories. And then you have 2 categorizations. So these 27 emotions also belong to 7 parent categories. So we can use both. And in fact, that's what we do. We train 2 models. One to only predict 7 labels, and the other one for 28 labels. And this is one of the largest emotion classification data sets with the most classes as well. So 28 labels is quite, you have very complex emotions. And we have split, as the original Go Emotions paper has done, 80% training, 10% adaptation, 10% test. So once we train this model, the next stage is to perform inference on song lyrics. So once we train, we have a model that can classify the emotion from any text there. And then we feed the song lyrics from these 2 large MIDI data sets that are not labeled. They're all black. MIDI data set and Reddit MIDI data set. And we have to filter it because not all of them have song lyrics embedded. So we have to go through each song to see if they have song lyrics. And then we have to filter them if they're English, because the data set for emotions is for English language. And then we further filter it to have at least 50 words. So in total, we have about 8,000 samples from LAC and 4,000 samples from Reddit. So 12,000 samples of lyrics that we can feed into this model. All right. So these are the results. Yeah, this is the training part on Go Emotions. So I'm not still at the inference part. This is not the song lyrics, this is the Go Emotions text classification data set. And the baseline model is from the original Go Emotions paper. It's BERT with 12 layers. Our model has 6 layers. And because it's a multi-label classification, we have to come up with a classification threshold. So, it's very easy to play with this classification threshold so that you balance precision and recall. So what I've done is to come up with a single value to use across all experiments. And for the 7 label data set, they worked out pretty well. It's very good balance. And for the 28 label, not so much. But in the end, what I'd like to focus on is the F1 score because it's not very sensitive to the classification threshold. So this is the 7 label data set. These are 6 basic emotions plus the neutral labels. So it's anger, disgust, fear, joy, neutral, sadness, and surprise. And then on the right-hand side, you have 28 labels. So I'm not going to go through all of them. But you have complex emotions such as optimism and pride and approval. So it's cool that we have this complexity of emotions. So compared to the baseline, our model performs almost equally on this 7 label data set, which makes sense. I mean, it's a smaller model anyway. For 28 labels, I'm very surprised that we outperformed this model by a small margin. So when you look at the macro average of the F1 score, so it's like a 4% improvement over the baseline. So I was surprised and I tried to come up with some hypotheses, and I would like to hear your hypothesis as well, how this could happen, because it's basically the same model and same data set. But then what I thought is, I'm using a smaller model, yeah? And because I have 28 labels, the output space is actually, it's a higher dimensional space. So there is more room for overfitting, maybe, because it's a more complex plane. So by using a smaller model, maybe it would work better as generalization. That's one of the hypotheses I came up with. And then we use these 2 models to perform inference on song lyrics. So this time I'm presenting you the result of the classification threshold of 0.1 so that you see all these emotions. And yeah, most of the songs are about joy. So these are pop rock music, Western pop rock music data set. So joy is a very popular theme, such as love and optimism, and also sadness, curiosity. So this is just to give you an idea of the distribution of the data that we come up with. And then let's see some samples for some qualitative analysis. So as I've given you the example of the song Imagine from John Lennon. And for example, it says, imagine all the people living for today. So when you feed this into a 7 label model, you get joy. That's the highest ranked emotion. But then when you feed it in the 28 label model, you get optimism. So I find this to be very cool because when you look at the song lyrics, it says, imagine all the people living for today. It's quite an optimistic view from John Lennon. Another one, Take a Chance on Me by Alpha. And for example, it says, if you need me, let me know, I'm gonna be around. So when you look at the 7 label prediction, again, it says joy, but the 28 label prediction, it says caring. So, it's a complex emotion, but actually when you look at the song lyrics, there is actually a caring emotion within the song. And finally, the song Are You Lonesome Tonight by Elvis Presley. And you probably know the song that says, Are You Lonesome Tonight, Do You Miss Me Tonight? Again, 7 label prediction says there's sadness, and 28 label prediction says there's curiosity. And in fact, the lyrics convey curiosity if she's lonesome tonight, but I don't think he's genuinely curious, just wants to get laid or something. But actually, Elvis Presley never wrote any songs, that's the joke. He just sang them. And so this is how the data set looks like. So I made this data set publicly available without any filtering or thresholding, nothing. So people can put whatever threshold they want, they can take any song they want. So how it looks like is I have, for every single song, I have the probabilities of every single emotion. And again, this is the multi-label problem, so these probabilities do not add up to 1. So yeah, you can get the data set, get the training models. So if you have the training models, you can use it for stuff other than song lyrics. You can use it for poetry, for example. But yeah, the data set that we created is publicly available. So as I said, you can use it to play it using any emotion or text any emotion. So it's quite flexible. And finally, to conclude, this is not future work, but it's relevant work that I presented yesterday. So this two works went in parallel, and we came up with another data set. So this time it's continuous labels. So here you have the valence arousal emotion representation plane. So in the previous, like in this work, previous work that I presented, you have discrete labels, yeah. But here you have a continuous plane. So you can, and this within this data set, you have for every single song, you have valence and arousal values, and then you can plug these into the song generation model, and you can create songs. And this one in particular, it has 34, almost 35,000, so it's larger than the previous one, and it's also a finer plane because you can have any emotion using these two valence and arousal coordinates. And that's basically it, and I can take your questions if you have it.
Thank you. Any questions?
Okay, I think it's a very interesting word. However, as far as I know, songs have no emotions. Listeners have emotions. And they depend, the same song can trigger very different emotions on each one of the listeners, and depending also on his own situation. I mean, depends on the memories attached to that song. Very different from mine. So I think to use this affective model, Russell complex affective model, maybe it's not the right way to do that.
But how about, let's say you have Go Emotion dataset, dataset from Google. You can make the same argument about that. Like you and I can look at different text and come up with a different discrete emotion, not from Russell. Yeah? You can think of it sad, I can think of it as kind of angry. So it's all relative.
Just one question. Did you find a correlation between your 28 label neutral state and your 7 label state where there's no neutral state? Just as a question, because on ABBA you got 47%.
But I don't look at it.
Okay, it was just a question. Okay.
And then he basically taught me and went to industry.
Okay.
So
No worries.
Okay. Have you thought about sites using the lyrics for emotion classification, also using BPM for the scales, suggesting your manual for emotion classification?
Yes, so the BPM, I'm thinking of using it, so it's the second part that I want to use, this temporal matching. So BPM is a part of it, and transitions is another part of it, scene boundaries or musical boundaries. Your second point, using major minor scales for emotion. So that was my fallback idea, that if this didn't work. And so it's a more primitive way of looking at it. Yeah, so you have major scale and minor scale, so you can say one is happy, one is sad, but then not always. Yeah.
And also, for instance, there are songs that have happy lyrics, sad lyrics, but with a meter scale, and it translates
Yeah.
stability because of that.
Yeah, I was exactly. Yeah, I like the second model a bit better. For example, I thought of the song "Every Breath You Take" by the Police. So it's like a love song, but when you listen to the lyrics, like every step you take, I'll be watching you. It's like a creep that's stalking a woman. Yeah. So it's not a love song, but it sounds like a love song.
Question here. So the objective is to create soundtracks for lyrics.
So yeah,
You don't have any melodic or harmonic analysis implemented in your system, right?
analysis. No, so I'm doing the analysis on the video side, and I'm doing the synthesis on the music side.
So it's just the lyrics that you...
You're talking about this work. Yeah, so it's the analysis on the... So actually, this work that I presented, I'm not doing anything about music. So I'm using music data, I'm using lyrics from the music data set in order to map them to each other. But the actual work is not doing anything with the music itself. Okay? It's just lyrics and emotions.
The objective is to generate music, right?
Yes, so that's this paper. Yeah.
So, if you want to create songs which are based on words, lyrics, like it's been said, things like sarcasm, recently just said, and even instrumental music, which sometimes transcends meaning of words.
Yes.
I think it's quite great with that, but how do we intend to incorporate that into
How do I intend to incorporate this work? I mean, yes, so we start...
the melodic content, because this is more focused on the
lyrics.
yes,
Yes.
it's more textual.
Yes, yes, yes.
So, and music, it's emotion, but sometimes it's not present.
Sure.
So, how do you implement that complexity with melodic and harmonic? Do you have any...
Sure. I mean, once you create a data set using lyrics, then you get the emotions, and then you make the assumption that the music and lyrics are connected. So you have the song with lyrics, yeah, and you have the music. So you can just throw away the lyrics because you already use the lyrics to create, classify the emotion. Then you can merge the emotion and music and throw away the lyrics. So in the end, you have an instrumental song, yeah, because there's no lyrics anymore. And then you have the emotion label. So then the songs I generate, they sound instrumental anyway. So you cannot, I don't generate lyrics anyway. So I only work at the generation step. I only work with music and labels. But this is for the analysis. I use lyrics as an intermediary to get to that point to have the emotion.
And now, Ugo, what's that first?
Okay.
Yeah, okay.
Just thank you for the presentation. Just a short question. Can you talk about the performance of the still bird system in Brain, because we just reduced the number of layers?
Yeah.
How did it go?
Yeah, basically, it's deep neural networks, yeah, so you only see the results, you don't know what's going on behind the scenes, so that was the result, like...
No, but the performance issues, how long did the data kind of machine can use?
So yeah, again, my master student trained it, so it didn't take very long, just a few days, I guess. But again, it's not significantly smaller, yeah, so it's, instead of 12 layers, you have 6 layers, so it's still half of it, but yeah, this knowledge distillation is quite cool that if you have some model that can only run on GPU, you can distill it so that it can run on CPU, and maybe even on phones or browsers.
Even for training and retraining?
Yes.
So, I understand the motivation, the lack of data sets and everything, but let me make a provocation.
Sure.
So, first you train a new model, and you compare it with the baseline, and there is a small improvement, but still at least to our 0.5. There are other models people should compare them, but let's forget that. Are you arguing that you're releasing a huge data set, but then in the end you have X part 0.5 useful and
No, I mean, no. So this was a parallel work, and in my second work, I actually, like, the way I go with it is I just use it to generate the music, and if it sounds good to my ear or other people's ear as well, it's good enough. But then at the end of this PhD, I want to have a human study where I would, give the music, and then it will be the emotion, but it will be hidden, and then the people would class label it and then see how well it matches. Yeah. So in the end, because there is this lack of data, again, like for example, I'm starting from lyrics. Yeah, lyrics can be different than music. And here, I'm starting from these labels from Spotify. They're also created on the raw audio. So the raw audio is different than MIDI. So all these labels, I call them weak labels. So they're not strong labels that are created by a human. So they are very weak. But the idea is if you have like 35,000 of them, you may have something meaningful in the end, and that I will analyze through human evaluation.
And I will also do this. So you have these very complex neural networks. It's not complex to use because you have all the tools nowadays that make it very easy, but what is underneath is very complex. Have you tried some more simple approach? I don't know, something simple, less simple, for instance, rule-based approach, less simple-based approach. I know it's very simple, but when you just have 0.5 action score, it's probably worth trying instead of having 2 or 3 days or whatever training you can do in like afternoon or so.
Yeah, I haven't. I mean, I don't have much experience on like old NLP methods, so I need to learn about it. If there's like a just plug and play method, I would love for you to share with me so I can do it. But otherwise, I have to sit down and learn the old NLP methods, you know. Yes. So I have to know the rules. But these lexicons like n-gram methods, for example, yeah, you have to look at like. Again, I don't know much about it.
Some machine learning, not deep learning, so some simpler methods, like Bayes and Clark, something like that, probably worth trying.
Sure, yeah.
You can do it in just a few hours.
Yes. Yeah, it makes sense. But one of the cool things is, so these stillbird or bird models, they are already pre-trained on language, yeah? So it's actually, I'm just fine-tuning it. So I have this huge model, but I'm not like training it from scratch. So if I do this, I will probably overfit. So I would probably have I would even have worse results. Because I'm fine-tuning it, I think I'm not just like being super exploitative. But you know, you have a very good point that
there are models that achieve better performance than in your emotions than when you do yourself. And that already tried
I tried some of the models, I couldn't find any good. But yeah, if you know,
I'm not sure.
Sorry, we have to move on.
all right. we can discuss it later. Yeah. Thank you.